Well, hello and welcome YouTube. Mr. Robbins back here with yet another brand new exciting video, all math basic course. And as always, it is an honor and a privilege to be serving you today, as it is every day here in my virtual classroom. Step on inside, and congratulations if you've made it this far in Integrated Math 2. I believe, to my knowledge, this is the last section of newly learned material in the text. It's section 11.7 on surface areas and volumes of spheres. So, I'm going to do the lecture portion of this thing. I'll just guide through that with the examples. If you want to download this PDF and check it out, check the description section down below for that, as well as the timestamp for when I start. Well, I'm going to start the lecture now, but if you want to skip on past that and go to the problem set, numbers, I think up to 47, you can find those ones down there as well. I still have some more videos to record to make up of some of the old stuff, but as far as playlist stuff goes, if this is the time of the year that you're watching this one, then fantastic, you made it this far. And still more like reviews and stuff for me to do, but new material is right here. So guys, I'm going to go ahead and get started with this right now, and we are going to find surface areas of spheres and volumes of spheres. New core vocabulary: chord of a sphere and great circle. Oh gosh, if great circle was the phrase that was used in some of those very enriching problems and I didn't know how to answer them, I hope those don't show up, because they're interesting. Anyway, I don't even know what we're going to use the chords for, but we'll see. A sphere is a set of all points in space equidistant from a given point. You think of a sphere like a ball, a baseball, a basketball, a volleyball, soccer ball. It's spherical in nature, a volleyball, a beach ball. This point is called the center of the sphere, so it's a 3D circle to people, a 3D circle. A radius of a sphere is a segment from the center to a point on the sphere. So this is a radius, but radius can go in any which set as long as it hits the sphere. So normally you don't see the middle, the center and middle, but that's radius like for a circle as well. A chord of a sphere is a segment whose endpoints are on the sphere itself. So this is, pretend like it's touching the surface here and there's just a straight segment going in between, very much like chords and circles. A chord of a sphere, oh, I just read that. A diameter of a sphere is a chord that contains the center. And I think that's just their way of saying it's the longest chord in the circle, that kind of thing. As with circles, the terms radius and diameter also represent distances, and the diameter is twice the radius. Cool. If a plane intersects a sphere, then the intersection is either a single point or a circle. So if the plane intersected the very top, or tangentially with the sphere, then it would touch a single point. Otherwise, when it cuts through, it actually creates a circle on there. If the plane contains the center of the sphere, then the intersection is a great circle of the sphere. That's definitely the phrasing I think that they used at the time. No, I think great circle was fine. What was the one? It was like spherical geometry. It wasn't great circle that was weird. It was spherical geometry that was weird. Maybe they showed great circle on it, and I got confused. The circumference of a great circle is the circumference of the sphere. So, yeah, a sphere's circumference is still the distance around it, the longest distance that you can have around it, like if we're talking equator of the Earth and stuff like that. Every great circle of a sphere separates the sphere into two congruent halves called hemispheres, and Earth has hemispheres as well. So right now we're just learning a lot of things. None of them have been formulas yet. I think it's just knowledge of terms, and they'll probably show up in example problems. Okay, surface area of a sphere. They're starting with surface area instead of volume. They're both brand new to us, and that's fine. This is probably one I could introduce with you first as well. Surface area is 4 pi r squared. Now, actually, they're showing you this. My favorite way of remembering this formula, and if it's something that you have to memorize, right, is I think of it like the uncovering of a baseball. Now, I don't know if you're aware, but a baseball is made up of two hides that are then seamed together around some core and stitched together. And each part, and I like what they're doing here, the leathering portion, the hide portion kind of simulates almost like a circle. So to understand the formula for surface area, think of a baseball. The surface area is shown from two congruent shapes, each represent two joined circles. There are great videos never mind. There are some videos that show how baseballs are made. And it's interesting, just to show like the love and craft in every baseball. It's not all machine. So the entire covering of the baseball consists of 4 circles, each with radius r. So yeah, I like to think of it as the area of 4 circles, and because it's the outside, I like to think of surface area that way. That's why I will absolutely, I'm a diehard baseball fan, but actually, no, Devil Wears Prada is in the background right now. But baseball is normally in the background for my stuff. I'll always think of it this way, and I will never forget surface area for sphere, just by thinking of it as 4 circles, the area of 4 circles. Anyway, so that's kind of what they're saying there. Hopefully we remember that, and I'm sure we're going to do examples right now. Yes. Find the surface area of each sphere. I guess they break down all the terminology so you know what you're looking at. In this case here, we have a radius of 8 inches. To find the surface area, we'll do 4 pi r squared. 4 pi times 8 squared rounds you out to 804.25 square inches. So they're going to use 2 decimal places again. Again, I'll let the calculations speak for themselves. This one here, you have a circumference of 12 pi feet. This is, I guess, their idea of talking about the great circle. And that great circle is the circumference that would give you the radius if you find it. So if the circumference is 12 pi feet, 12 pi equals 2 pi r. Divide both sides by 2 pi, you get your radius of 6 feet. Now that you have your radius, you can use the formula again, and you get 452.39 square feet for that surface area. So surface area, again, is what you cover on the outside of it. Finding the diameter of a sphere. Well, this is an example. I thought they were going to teach us. I'm like, well, we already talked about it. If you get the radius, you can double it, and that's what they're going to do here. So they tell you the surface area this time. That's S. I normally write SA, probably incorrectly. And you solve for R. They do a square root of both sides kind of thing, and they solve for R. It looks to be exact at 2.25 centimeters. And then you double that. You double 2.25, you get your diameter of 4.5 centimeters. And I'm going quick through these because they're already written, and we're going to do our own problem sets later. Some monitoring progress, I tend to skip those because we're going to do our own. Finding volumes of spheres. What's all this? Let me read this first soundly. It's really interesting, actually. Honestly, I don't know what you're going to get out of this necessarily. I'm going to skip this part. It's very enriching. It shows a proof for something. I do volume through calculus as well, and they're not going to show you calculus in integrated math too. So let me get to the formula. Okay, the formula for the volume of a sphere is 4/3 pi r cubed. 4/3 pi r cubed. It seems a little different. I see almost 4 pi r squared. You almost see the pi r squared thing with that. So again, something to memorize and stuff, I guess, a little bit. One thing I do want to bring up is they talk about the volume of a hemisphere is 2/3 pi r cubed. Because 2/3 is half of 4/3. It makes sense that that's how we would say hemisphere. Half of 4/3 pi r cubed is 2/3 pi r cubed. So we'll use that if they ask us to use it. We only have radius in this one. We only had radius in the other one. Spheres don't have heights. It's all radii. It's all radii because it all has that circular nature. So find the volume of a soccer ball with a radius of 4.5 inches. So 4/3 pi r cubed is the way. So you see that right here. The volume of the soccer ball will be that. I'll let you just take a look at that and what it's doing. We're substituting, and then we're going to approximate afterward. 2 decimal places will be the way to go. Find the volume of a sphere if you know the surface area. Okay, so because volume and surface area both use radius in their formulas, use the surface area to get the radius, then use the radius to get the volume. So if your surface area is 324 pi, divide both sides by 4 pi, and then take the square root of both sides to get 9. That's the radius that you use in 4/3 pi r cubed, and then you can get its volume. So there is a relationship you can determine after you do all that work. Finding the volume of a composite solid, it's a lot more of the same as what we did before, but now that they're going to include spheres, it's not very often that you use a sphere in a composite solid to add or subtract, but hemispheres are very common. So taking a hemisphere out to kind of make this like bowl configuration inside the cylindrical shape, that is, notice how they're taking 1/2 of 4/3 pi r cubed to get 2/3 pi r cubed. That's that volume of the hemisphere. So we're going to take the hemisphere out of the cylinder. Remember, cylinder's area base, pi r squared, times height. They give you a radius of 2 inches and a height of 2 inches, so it works itself out there. And the radius is the same for the hemisphere as it is for the cylinder. Notice the 2 inches can also be used right up there, and you get 2 inches for either or. So they work some stuff out. They go for common denominator to get an exact answer. That's a little unconventional of them, considering their answers always end up this way. So it depends if you want to type that in or type this in or do the work to get that. But you get 8.38 cubic inches. This is volume, so we are going to do cubic inches for that. And then this one right here, I'm not going to do the problem, but you can see right behind me. It kind of looks like that ice cream cone kind of look. And I think I brought that up. I teased it before. Excuse me, ice cream. It's like the volume of the cone plus the volume of the ice cream inside. So that's a hemisphere that's going to be added to the volume of this cone. And volume of a cone is 1/3 area base times height. I'll let it work itself out. You can pause and try it, but I'm going to move forward. And we move forward to the problem set on 11.7. So we begin with problems 1 and 2 in the vocabulary and core concept check. When a plane intersects a sphere, what must be true for the intersection to be a great circle? It must intersect with the center. It must intersect with the center. To intersect with the center, then you can start doing things like circumferences and stuff like that, because the center includes that radius all the way around like a disc. And it's the longest one. It includes the diameter and things like that as well. Number 2, explain the difference between a sphere and a hemisphere. A hemisphere is half of a sphere. That's its definition. A hemisphere is half of a sphere. They didn't talk about surface area of a hemisphere. I don't know if I want to bring it up. It's not really for this problem, but you have to remember that a hemisphere, it depends on the problem, but you have to remember that a hemisphere is half of a sphere, but we never talked about whether it includes the bottom. Sorry about that. This could be a hemisphere right here, and the surface area includes the top portion, but sometimes you might have that bottom portion, which means you might have to add a pi r squared to it. So I'll bring that up if it does come up. I don't know. We will do surface area of spheres themselves. Then we'll talk about hemispheres if they show. Without further ado, guys, though, we are going to get into this official problem set, numbers, I think, 3 through 47. So let's see what we have in store for us. Let's get the pen ready. Starting with problem numbers 3 through 6. Find the surface area of the sphere, not hemispheres, but just a sphere. So problem, the surface area formula will be 4 pi r squared. R is the radius. And this radius on number 3 you see is 4 feet. So if the radius is 4 feet, the volume will be 4 pi times 4 squared. I'll always try and get exact answers for you. 4 squared is 16 times 4 is 64. So you get 64 pi square feet, and it is square feet. This is area. So I'm going to take my calculator out and do 64 pi, not for you to see, for you to maybe try. And I'm going to round to 201.06. And I've probably said this before. If I didn't have to do calculator work to round these, oh, not centimeters, what am I doing? If I didn't have to use calculators for these things, I'd probably be done a lot faster in a lot of these problems. It's one thing if I had a calculator in hand, and I still don't know to this day why I don't just use a calculator. I guess because then you can't see it. But it would be so much faster than me doing the mouse clicking that I do, especially when the emulator is acting up. Or it's behind a bunch of windows on my thing. Number 4, 7.5. That is still a radius. This 7.5 centimeters, just because it's not on the great circle that's drawn, doesn't mean it doesn't have its own great circle to work through, because it's still going through the center. It's from center to the surface of the sphere. So it's still a radius of 7.5. So volume is 4 pi times 7.5 squared. And I don't know 7.5 squared. I don't remember. I'm sure I've seen it. Let's see. 56.25. In my head I had 50.25, but in my head I was saying that sounds too small. Now that number times 4 is 225 exactly. So I get 225 pi square centimeters for this. Oh, I've been writing volume. Oh my goodness. Each time I said surface area, I might have said volume, but I'm so sorry about that, guys. This is surface area, surface area. Let's patch that one up. Cut and redo action. Please change those. Please change those. So that's surface area. And let's go ahead and round that thing. You're probably, again, yelling at the screen. I don't know. I can't control what you're doing. So 706.858. So 706.86 square centimeters when not in terms of pi, and you multiply by pi. Number 5, this time we're referring to a diameter. Again, just because it goes through the center means that we can do that. It doesn't necessarily have to be on the great circle for that to happen. So if the diameter is 18.3, the radius would be half of the 18.3 meters, which would be 9.15 meters. So if the radius of 9.15 meters, we'll find the surface area, which is 4 pi times 9.15 squared. Definitely don't know what that one squared is, much less what it is times 4. That'll give me 334.89 exactly. So 334.89 times pi square meters. When you round it, you get 1052.09 rounded. 1052.09. Oh, square meters. Okay, that's the first 4 problems. Oh, the first 3, excuse me. The first 3 problems. Let's do the last of the 4 problems. And this time you have the great circles circumference, which means we can use that to find the radius. So circumference is 2 pi r, so 4 pi equals 2 pi r. If you divide both sides by 2 pi, pi's cancel, and 4 divided by 2 is 2. So your radius is going to be 2 feet. 2 feet exactly. So the surface area of that guy, 4 pi times 2 squared. 2 squared is 4 times 4 is 16. You get 16 pi. This is square feet. And that will approximate to 49 or 50 something. 16 pi. 50.265, so 50.27 square feet. Okay, that's numbers 3 through 6 on surface area of sphere. Now we're going to find, in numbers 7 through 10, different things, radius, radius, diameter, diameter, based on information provided. They still want to stick to surface area. Volume is to come momentarily, I'm sure. Number 7, find the radius of a sphere with a surface area of 4 pi square feet. So if the surface area is 4 pi and this equals 4 pi r squared, we have to find the radius based off that. If I divide both sides by 4 pi, it may cancel here, but here it becomes 1. Canceling means, in this case, becoming 1, but 1 times r squared is still r squared. 4 pi over 4 pi is 1. If r squared equals 1, then r is 1, and this is in feet. R is 1 feet. 1 foot radius that we find. Number 8, more of the same. Literally, there's really nothing that we can change on what's going on here. Radius, 1024 pi is 4 pi r squared. We will divide both sides by 4 pi. And the pi's are gone, but 1024 divided by 4 remains, and that's 256. You can take the square root of that and get 16 as an exact answer. This is in inches. That is your radius. 7 and 8. All right, number 9, let's find the diameter. So the diameter will be found if you double the radius. So we got to find the radius first and then doubling. Surface area is 900 pi. At this point, we understand with 4 pi r squared is the formula. We will divide by 4 pi. Pi's cancel. 900 divided by 4 is 225. 225 is r squared. Take that square root. Take that square root. Take the square root of that and you get 15. That's 15 meters. Now the diameter will be doubling that 15 and you'll get 30 meters. And then lastly from this section here, number 10, and I recognize I'm going quickly. I'm just letting the calculations work themselves out. Once you're set up and you understand strategy, game plan, then you're probably pretty good. So 196 pi square meters is the surface area here. I will divide by 4 pi. And 196 divided by 4 is, not 48, 49, is 49. That's also a perfect square. So they've been very helpful. So r is going to be 7. That's 7 centimeters. That's your radius. The diameter will be double the 7 centimeters, which is 14 centimeters. Okay, that is numbers 7 through 10. Now we move on to numbers 11 and 12 where we find the surface area. Oh, they do give it. Okay. I don't know if this was actually a part of the problem set thing, so there's a little bit of enrichment here, and it's this. Surface area itself of a sphere, this is not just number 11, but just in general, is 4 pi r squared, but the surface area of a hemisphere can be one of two things. Understand that it should be half of a sphere, so 2 pi r squared would absolutely be a part of it. However, when the base of the hemisphere is not covered, then the base is a part of the surface, just like cylinder. Well, we didn't do surface area cylinders, but just like cones were. Cones were not just the party lateral facing, it was also the bottom base. And 2 pi r squared, the radius they're referring to is this one, for example, and that's the same radius that's the base of that circle. That means you can add, potentially, and in these problems, I believe you should, an additional pi r squared, the area of the base. So this is, I don't know if you actually call it lateral area, but it's the actual dome portion plus the area of the base. And 2 pi r squared plus 1 pi r squared can equal 3 pi r squared. And this is really what I'm going to work off here. Generally, 2 pi r squared is the one to consider if you only just have that dome, the half dome portion, or whatever I want to call it. We will include this base, though. It will be added. I'm going to use 3 pi r squared for this one. So the surface area of this hemisphere is going to be 3 pi times the radius squared. The radius is 5. So 5 squared is 25 times 3 is 75. You get 75 pi square meters. and 75 pi calculates. Ooh, the calculator turned off on me at the very instant that I was going to go to it. 235.62. 235.62 square meters. Okay. Number 12. Same-ish when it comes to that bottom portion. I will be including it, so I'll do 3 pi r squared, but we have to first find the radius. We have the diameter of 12 inches, so the radius will be half of 12, which is 6 inches. So the surface area is 3 pi times 6 squared. 36 times 3 is 108. And 108 pi. 339.29. This is inches. 339.29 square inches. Okay. All right, let's keep moving forward. Find the volume of the sphere. Now we're hitting volume sense. Some things will probably sound repetitive. What it actually looks like, if you can tell. 2 sets of radii, 2 sets of diameters, 2 sets of circumferences. So I would challenge you, if you're a viewer watching and you're trying to, come up with, trying to figure out how to do it. Watch me do the odd, then try the even. Or, watch me do the even, then try the odd. Try, it's not just to watch and copy down, I hope. And hopefully you can learn some stuff, but try it after that. So we get a radius of 8 meters for this set, and the volume is 4/3 pi r cubed. So pi times 8 cubed. This is where, I'm less inclined to write exact answers here and there just because some things won't simplify very well. Now, 8 cubed, I believe, is 512. Yep. Times 4, I believe, is 2048. Yep. So we got 2048 over 3 pi cubic meters. That is the volume of this guy. Now, we will go ahead and round that. 2048 does not divide by 3, by the way. And you get 2144.66 cubic meters. There's one. Let's move on to number 14 with 4 feet. I could tell you the answer right now, as far as because this is half the size, I can take my previous volume and divide it by 8. I'm just going to hit my divided by 8 button on my calculator. I'll show you what this looks like, and we'll see if this is what we get. Keep in mind that the answer now is a different cubic measurement. It's like cubic feet instead of cubic meters, but we should get this answer here. Because a volume, you cube the similarity ratios, and because we're talking about radii for both of these, this radius is half of that radius, different units, but the number is half of it, so we got to cube 1/2 to get 1/8. We should be dividing by 8. Anyway, just an interesting thought based on what they gave me there. So let's go ahead and say we got a 4-foot radius. The volume is 4/3 pi times 4 cubed. 4 cubed is 64, and 64 times 4 is 256. So we'll get 256 pi over 3. And I'm going to go ahead and calculate that. 256 pi divided by 3. Oh, come here. You, come here. Great. Take a close look. Okay, right here. And stop. All right, so they're the same, right? So we'll say 268.08. So that was a similar solids thing that I kind of worked out, if that makes sense. That's what I was going with there. So cubic feet, and that is the answer to number 14. Number 15 and 16, both diameters. I wouldn't dare bother with the similarity ratio of these two because it's kind of it's an awkward one. It's not like 1/2. Diameter is 22 yards, which makes radius, which we need 11 yards because we must. Okay, we divide by 2, but we must use that in our volume formula. So 4/3 pi times the radius cubed. I believe that's 1,331. So multiplied by 4. I'm going to let my calculator do that. 11 cubed. Yep, 1331 times 4. 5324. So this ends up being 5324 over 3 pi. This is in cubic yards. This also cannot, divide evenly or reduce, and it's okay because we're going to be multiplying by pi anyway. So this thing's going to round to 5575.28. 5575.28 cubic yards for that guy. Yards cubed, as the kids would say. Number 16, 14-foot diameter means a 7-foot radius. And now we do our substitution. 4/3 pi times the radius cubed. 7 cubed is 343 times 4 is something. I'll make sure. 7 cubed, 343 times 4. 1372. 1,372 pi over 3 cubic feet. You might notice that as we divide each time by 3, see, pi is 3.14. So our answers aren't generally that much bigger than the thing we had before. Notice the other number was 1372 pi over 3. Now when we round this, this is 1436. I know that it's different. Clearly it's different. It's not like I'm going to get, oh, sorry, I have to round this. 0.76. 0.76. Part of what I'm saying, I guess, and it's not a really big thing, but to feel like you did something right, it should be just slightly larger than this. And this is only 60 cubic feet larger. And this is slightly larger than that number and that kind of thing. But that's just in the final calculation. That doesn't mean you did everything right beforehand. Just so you know. Numbers 17 and 18, we now have the circumference of the great circle. So we're going to find the radius here as well. The circumference equals 2 pi r. We would divide both sides by 2 pi here. And pi's cancel, 2's cancel there. You're left with the radius of 10 centimeters. Sorry, I should have set this up by saying the circumference was 20 pi centimeters. Circumference equals 20 pi centimeters. Okay, so the radius is 10 centimeters. The volume, once again, 4/3 pi r cubed. None of these could actually divide by 3. They never actually reduced in these. 10 cubed is 1,000 times 4 is 4,000. So I get 4,000 pi over 3. Very clean looking number. So this number will be something more than 4,000. And 4,000 pi. 4188.79. 4188.79 cubic centimeters. A lot of drill and kill so far with these. I hope they're feeling pretty good. The sphere stuff isn't all that difficult as an overall, but I speak too soon. We're probably going to hit some word problem things that are a little challenging. This time the circumference is 7 pi inches. I feel like this won't be too clean, but number 18, with the circumference of 7 pi inches, we now dive into 7 pi being equal to 2 pi times the radius. If you divide by 2 pi here, sure, the pi's go away on this part, but you also still get 7 halves. That's 3.5. So 3.5 inch radius. We'll use that in our volume formula. Actually, this one should be pretty clean looking. Check this one out. 4/3 pi times 3. Oh, I don't know 3.5 cubed. I know 3.5 squared. Never mind. I don't actually know how clean or not clean this will look. 3.5 cubed is a little less clean, and when I multiply it by 4, it's 42.85. When I multiply it by 4, I get 171.5. Not too shabby. So 171.5 pi divided by 3. So this number will be a little more than 171.5. 179.59. 179.59. Oh, this is cubic inches. And that is number 18. So good old drill and kill there. I am pretty good on time, still under the half hour as of so far. We have 47 problems to do, and those were the drill and kills. We're probably going to get to longer ones now. Numbers 19 and 20. Find the volume of the sphere with the given surface area. 19. So the surface area is 16 pi square feet, which means that 16 pi is equal to, surface area is equal to 4 pi r squared. We're going to use the surface area formula to get the radius of this so we can then get the volume out. When I divide by 4 pi here, I get the radius squared being 4, and take the square root of both sides. You get 2 foot radius for the set, so we can now use that to find the volume. So volume being 4/3 pi times 2 cubed gives me, now this was in terms of pi. I think it's acceptable that I can put my answer in terms of pi as well. So 2 cubed is 8. 8 times 4 is 32. I get 32 pi over 3 cubic feet. So we get the radius. We use that to get the volume. I'll do it in terms of pi because theirs was. I think that's fair. Number 20. Surface area equals 484 pi square centimeters. 484 pi equals, formula, 4 pi r squared. Remember, this is a sphere, not a hemisphere. Divide both sides by 4 pi in this case. We get 121. That's also a perfect square. They've been very nice with clean numbers so far. So r is 11 centimeters. That's our radius. We use radius to get volume, 4/3 pi times the radius cubed. I'll get you the exact. I just don't. We did this before. This might be the exact same number as something before. I just don't recall it. 5324. 11 cubed times 4. 5324. 5324 divided by 3 times pi, and this is cubic centimeters. I think that was the same value that we had previously. I don't know if it was for surface. It must have been for volume to cube it. Okay, there are only so many numbers you can get perfect cubes of. Let's use one. Error analysis. Describe and correct the error in finding the volume of the sphere. 4/3 pi times 6. Oh, this should be cubed, not squared. I assume the rest of the math will be correct, and I assume we're going to have to correct it. It does say correct the error. So their formula is wrong. I'll just, instead of typing, wrong formula should be volume equals 4/3 pi r cubed. So let's go ahead and correct that. Let's do the cubing. So the volume is 4/3 pi. They used the radius. The radius is 6 feet. So we're going to cube that guy. 6 cubed is 216. 216 can divide by 3. This is the first one. You get 72. And 72 times 4 is 288. So if I'm correct, this would be 288 pi. Now, I will get to that portion in just a moment. What I'm going to do is type out 4/3 pi 6 cubed. Now, the way that I'll know that I'm right is if this is only a little bit more than 288 as an answer, because we are dividing by 3. No, I take it back. We're just multiplying by pi. So my answer should be somewhere in the probably 900s, 800s, 900s. Let's see. Yeah, 904. Okay, so I feel like I had the right number with what I was doing on the calculations, so I'm going to trust my own work on that. So this is 904.78. What were the units? Oh, feet. So this is cubic feet. This is cubic feet. It's like that was the error. They didn't leave units. Okay, number 22. Also error analysis. Describe and correct the error in finding the volume. Oh, did they ask for volume or surface area? Okay, they did ask for volume. Good. The volume of the sphere here. I'm already catching a mistake. They do cube this time, but what do? They use 3. 3 is not the radius. 3 is the diameter. Now, I could, if their number is correct, I could divide it by 8. Take half of it. I could divide it by 8, so I think the answer is going to be somewhere around 12, 13, maybe around 13, 12, 13, I don't know. I can't do that math in my head suddenly. 13 or 14 maybe. Anyway, let's do it. Number 22. Used diameter instead of radius. I guess 14 or something. 14 point something. All right, so use diameter instead of radius. That's what that says, radius. So the radius is half of 3, which is 1.5. So the volume, 4/3 pi times 1.5 cubed. I don't know 1.5 cubed. I'll just kind of do everything at once. Multiply is 3.375. Multiply it by 4. I get 13.5. And let me write it like that first. So the volume is 13.5 over 3 pi. Now, if I'm writing this as an exact answer, I don't accept decimals with fractions generally. So I'm going to multiply top and bottom by 2 because 13.5 doubled is 27. So I get 27 over 6 pi cubic inches, which will make sense if this answer is probably around 14 actually. So that volume, let's do 27 over 6 times pi. 14.137, so 14.14, 14.14 cubic inches. I dig it, I accept it, I believe it, because I also could have divided theirs by 8 because I divided this by 2 to get radius. Okay, we have some composite solids to find the volume of. They all include hemispheres. None of them really include spheres. Now, remember, before the surface area of the hemisphere I used was 3 pi r squared. This time I'm going back to 2 pi r squared for hemisphere because there is no base that's being talked about for several reasons. Either this is part of a hollow section here, so it's like a bowl configuration. You're looking at just the surface on the inside part, or it's being covered like this ice cream one. The base area here is being covered. Oh, we're doing volume. Ignore everything I just said. We're doing volume. Let's go. I just realized again, we haven't found surface area of a cylinder before. So let's go do volume. Here we go. We got an object 1 and an object 2. Maybe I'll copy and paste some of these guys over. We're doing volume. Okay. So you did hear something, though, that will be important for IM3. If a surface is covered, it doesn't count as a part of your surface. Anyway, so object 1 will be the cylinder. Object 2 will be the hemisphere. And it is a hemisphere. So the volume of this cylinder, object 1, is area of base times height. The area of the base of object 1. Let me just write everything. I forgot how I got to organize all my work here. The radius as an overall, y'all, is 5 inches. That's the radius for the cylinder as well as the hemisphere. That's 5. Now the height of object 1 is 9 inches. So these are the two parts that we need. We need the area of the base as pi times the radius squared, 25 pi square inches. And the height goes in with the volume where we get area of base Sorry. I hate when my undo button just undoes like an entire dissertation of work. Area of base times height. That's 225 pi square inches. Let's leave it exact for now. Cubic inches. Okay. The volume of object 2. It is 2/3 pi r cubed, and the radius that we're still using is 5. 5 cubed is 125. You double that, you get 250. So I get 250 thirds pi. So when I do volume 1 minus volume 2, I'll get the volume of the total. So volume total, it's not a frustum, but it is a subtraction. Volume 1 minus volume 2, which means we'll take 225 pi and subtract 250 thirds pi. Now 225 can be getting a common denominator here so we can combine things. You could also use the calculator at this point if they just want you to round. And you get 675 thirds pi and subtract that 250 pi, 250 thirds pi. And then here you get 425 pi over 3. This is cubic inches. Now that approximates to 445.06. 445.06. That is cubic inches, y'all. We got it. So remember, with the composite solid stuff and a hemisphere is half the volume of a sphere. So with that in mind, that should be kind of what we're working out there. 2/3 is half of 4/3. And that's what we do there. So again, these are all those hemispheres. So it's another 2/3 pi r cubed. And they share the same radius as this time the cone. Number 24 in this ice cream configuration, let's start with the hemisphere as object 1 and then the cone as object 2. So the radius of either object is 6 feet. So let's begin. The volume of object 1 is 2/3 pi r cubed, which is 512 thirds pi. 512 512 should be able to divide by 3. Did I get that right number? It's not 512. It's 530, not 520, sorry, 532. I don't know if that's right. What's 216 doubled? 432. I was thinking of 256 doubled, not 216 doubled. 432. Not, I was saying 512 should be divisible by, it shouldn't be divisible by 3. But this number should be divisible by 3 because I'm cubing a 6. 6 can divide by 3, so can 3 6s multiplied. Anyway, 432 divided by 3, I want to use my calculator for because I don't want to get it wrong. 432 divided by 3, I should be using the calculator to begin with. 14. 432 divided by 3. 144. So this is 144 pi cubic feet. I'm sure you're watching this like, why did I choose to watch this guy's channel? So that, I'm not going to round it yet. That's the object 1. Object 2, we have a height of 12 feet, and we have a cone. So the volume of object 2 is 1/3 area. Oh, let's do area of base here. Area of base is pi times 6 squared, which is 36 pi square feet. So 1/3 area of base times height. 1/3 of 36 is 12. 12 times 12 is 144. So we are going to take, wait, we got 144 pi. Oh, I guess it's okay that they're the same. We're not subtracting them, we're adding them. I was like, we're going to have a volume of 0, guys. No, apparently the volume of the hemisphere is the same as the volume of that cone. Interesting. So the volume of the total is the volume of both of those. 144 pi plus 144 pi, and I'm trusting that all my math is right, is 288 pi. And I might have done 288 pi before, but I don't remember it, so maybe I didn't use it. 904.78. That does sound a little familiar. 904.78 cubic feet. Cubic feet. So, yeah, it's conceivable and possible that a sphere and a cone can have the same volume. You just need the numbers for it, and I don't know how much of a coincidence that is. Sometimes they go, good, let's do something with them. I wasn't subtracting the volumes. I do add them in that case, and that way the answer is not 0. All right, number 25, we have a cylinder. It's on its side, and we do have a hemisphere. Now, with the hemisphere, just kind of keeping intact with the section and what we're talking about, I'll make it volume 1. The radius in either case is 10 centimeters. Now, the volume for object 1, the sphere, is 2/3, is 2/3 pi times the radius cubed. 1,000 times 2 is 2,000, so we get 2,000 pi over 3 cubic centimeters. The volume of object 2 will be found by doing some stuff. We got to find the area of the base and establish the height. The area of the base is pi times 10 squared, which is 100 pi. The height of object 2 is 18. You see, the height isn't 10 or 20. We don't look straight up and say this is height. This is radius. The height is the distance between your bases in your cylinder. So the height is actually 18 in this case for the cylinder. If I brought this thing up, see, this thing fell over. I got to bring it back up again. That'll be the height. So the volume of object 2 is pi, the area of the base, times the height, and you get 1,800 pi cubic centimeters. So if I'm going to go in exact answer mode, I can. I have 2,000 pi over 3. I'm going to add these. The volume of the total is 1,800 pi, the object 2, plus object 1, 2,000 pi over 3. If I multiply top and bottom here by 3, and that doesn't really look like a pi there. Oh, I'm missing pi. That's a plus. I said, my plus is looking like my pi is looking like a plus these days. So 1,800 pi, because these should be able to combine once I get a common denominator. So that's going to be 5,400 pi plus 2,000 pi, all divided by 3, which is 7,400 pi divided by 3, which you can't divide it by 3, but when I divide it by 3 and multiply it by pi, I get 7749.26. cubic centimeters. Cubic centimeters. So 7749.26 cubic centimeters, all should be good there. Let's move on to number 26. Now 26 has an interesting thing here. It has a cylinder and two hemispheres. What happens when you put two hemispheres together? You get a sphere. So what I'm going to do instead of putting the two hemispheres and doubling it, let's do the doubling now. Let's just treat it as one hemisphere. Let's call it object 1. It's the same radius either way. It's 6 meters. So with a radius of 6 meters, even for the cylinder, let's find the volume of the hemispheres. Volume of object 1 is going to be 4/3 pi r cubed. Okay, so we will, 6 cubed is 216. Let's divide it by 3 first this time. 216 divided by 3 is 72. 72 times 4 is 288. Oh, we get 288 pi again. How many times are we going to get 288 pi? Keep in mind, this is a part of a larger ensemble as an overall, but very, very classic values. Now, this is object 2, the cylinder in the middle. It does have a height, and I mentioned this before, distance between your bases. It does have a height of 14 meters. So the volume of this guy, let's find the area of the base. The area of the base of the object is pi times 6 squared, 36 pi. So the volume will be area of base times height, and 36 pi times 14, 36 times 14, is 504. So I got 504 pi cubic meters on that guy. We are going to add these two volumes together because this is both hemispheres together as one giant sphere. So volume of the total equals 288 pi plus 504 pi, which is 792 pi cubic meters, and that is rounding to something in the 2000s. 2488.14. 2488.14 cubic meters. All right. So lots and lots of calculations going on with those things. I hope that they're making sense with what we are doing. Questions? Ask in the comment section below if you need to. All right, let's keep moving forward. In exercises 27 to 32, find the surface area and volume of each ball. I guess this is how we get to put everything in real world terms or applications, especially if they actually measured these things appropriately. I could tell you the softball circumference is correct. Anyway, bowling ball has a diameter of 8.5 inches. So if the diameter 8.5 inches, then the radius will be half that diameter, which is 4.25 inches. We have to find both the surface area and volume. Let's start with surface area. That is 4, all these are 4 pi r squared. So 4 pi times 4.25 squared. I don't think they're too interested right now in exact answers, especially when the number's like this. So I'm going to go straight into the calculation. I hope that's okay. So 4 pi times 4.25 squared. And you can still get it. This rounds to 226.98 square inches. That's surface area. We need volume now as 4/3 pi times the radius cubed. And I wish there was a faster, there is, but I wish that I utilized it. I think I'm going to. Give me 1 second. Pi cubed times pi. I hope I did that correctly because my order of operations was a little weird on that, but I'm getting 321.56 cubic inches. What I'm going to do here on my graphing calculator, so you know how fast why I'm getting things super fast here on out. So I'm going to make 2 equations for these things. I'm going to make one for 4 pi times x squared. X is representing my radius, so as long as I get it, then I know that I'll be fine with it. And the other one will be 4/3 pi times x cubed. And all this stuff is laid out actually appropriately, so it should, order of operations wise, do what it wants to do. And I'm going to ask for certain values here in a table. This is possible for you to do in a scientific calculator, some of them at least, so long as you have to change different equations. But now, anything that's y1 is the answer for surface area. Anything that's y2 is the answer for volume for this. So the previous question, number 27, these are the numbers I should be getting. 226.98, 321.56. I'll plug them into there so you wonder, how'd you get it so fast? That's how I'm going to get them that fast. But I'm still going to write out this, just not the exact answer necessarily. All right, number 28. So number 28, the basketball has a circumference of 29.5 inches. Now, circumference is 29.5, and 29.5 equals 2 pi times your radius. The problem here is when you divide by 2 pi, I can clean up a little bit of this thing decimal-wise, but that pi is still going to be in the denominator. So 29.5 divided by 2 can clean up. That'll be kind of the top number. So I'll get 14.75, I think. So 14.75 divided by pi is my version of my radius I'm going to use. So for surface area, I'll do 4 thirds. No, excuse me, 4. I don't know why I didn't know the formula. 4 pi times the radius. I'm still questioning whether 29.5 over this is 14.75. I think it is. Pi r squared, and that'll be something. Won't that be something? And then the volume is 4 thirds pi times the radius cubed. Which, wouldn't that be something? Let's check them out. So I'm going to go, I'll show you my calculator one more time, and then after that we'll just kind of assume I'm doing it the way you want me to. So this one I'll do 14.75 divided by pi. That's an exact answer, and it's good. Do not round that one early, please. 277 point, and by the way, this thing's rounding these numbers. See how it rounded to 0.01, and this one rounded to 0.53. So it rounded up based on what you saw there, and that's what you should be doing. So surface area, 277.01, that's square inches, and the other one, 433.53, volume. 433.53 cubic inches. Okay. Number 29. Softball. I'm actually intrigued by finding out these ones because I coach it. Even in baseball. Circumference is 12 inches. What was the circumference of this one? 29.5. Okay. Circumference of this is 12 inches. 12 equals that 2 pi r. We're going to divide by 2 pi, and you get this time 6 over pi, right? We are dividing 12 by 2 to get 6. We're dividing by the pi, and that's what we get there. This is the radius of a softball. Not a beautiful number. Looks like it's a little less than 2 if you actually divide it with pi. So the surface area is 4 pi times 6 over pi squared. And the volume is 4 thirds pi times 6 over pi cubed. Handy dandy calculator will come into play. Hopefully come out to play. I'm trying to delete my previous entries. Give me 1 second. All right, 6 over pi is what I'm going to substitute into that. And it will calculate those things for me. I get 45.84. It says 0.837 on there because I have the room for it to say it. So 45.84 square inches. And then 29.18. 29.18 cubic inches. You know where I could have fault when it comes to rounding, by the way? Let me show you this calculator thing again, actually. Here's where I could have fault. So I said this will show 3 decimal places this time because there's room to show it. The last numbers were 3-digit numbers, and it cut them out. I could end up having rounding errors somewhere. Remember, this number, this 7, is a rounded thing. Maybe it was 0.65 or maybe it was 0.72, but this was rounded. This was 0.8366. What if something kicks up from a 4 to a 5 in the thousandths place, so it makes me kick this hundredths place number up because I'm rounding the thing? That's very possible, so I might have to look at some of these decimals to be sure that that's not what's happening. If I ever see something say a 0.5, I got to take a look and make sure that that's not a rounded value before. That's why you need the entire decimal of the thing when you're actually doing those. All right, number 30, golf ball. A golf ball. Diameter is 1.7 inches, which can allow us to get the radius by dividing it by 2. So radius is 1.7 over 2, which is 0.85 inches. Very, very small. So surface area, 4 pi r squared, and volume, 4/3 pi r cubed. If you don't think you've gotten enough practice with volume and surface area, both spheres and hemispheres, you crazy. 0.85. 9.08 is what I want to do for the first one. 9.08 square inches. And the volume, 2.57 cubic inches. That sounds right to me. Okay, number 31. Volleyball. These are pretty much all the different spheres that I named when I said, we know spheres. They're pretty much the same. I don't know if I said bowling ball. Volleyball circumference is 26 inches. So the radius will be found with 2 pi r. 26 equals 2 pi times the radius divided by 2 pi. This time, 26 over 2 is 13, and you get 13 over pi. This is in inches. So surface area, 4 pi times 13 over pi squared. And volume, 4/3 times pi times that radius cubed. Okay, so 13 over pi. Oops, I typed 13 pi. 13 over pi. Did that work? 215, this is surface area, 215.18 square inches. Let me fit this over here just a little bit. And the volume, 296.8, I need to find another number, 296.80 cubic inches. Did I not round when I had 3-digit numbers before? Did I only round to 1 decimal place? No, I never did. I wonder how I got the number of decimal places then. This one cuts off a decimal place for some. Oh, because it's a 0 probably. That's okay. That makes sense. All right. Now, anyway, you can't see my screen with that. I'm just looking at my screen. Last one from this set, number 32. Find the surface area and volume of the baseball with that's correct as well, 9-inch circumference. So, I'm like fact checking the book. So 9 inches equals 2 pi times the radius. I'm going to leave this as 9 over 2 pi. Actually, I'm going to write it as 4.5 pi. 4.5 over pi. Wait a minute. 4.5 over pi. I was thinking about if there was a previous problem where I did something like this with it, and we're good. So that many inches. Okay, so surface area, 4 pi, 4.5 over pi, squared, 4 pi r squared. Volume, 4/3 pi times 4.5 over pi cubed. This is what they think of every time they make a baseball. Okay, so 4.5 over pi gives us surface area rounded to 25.78. I'm running out of room. 25.78 square inches and a volume of 12.31 cubic inches. Okay. Okay. That's the bottom of that page. Let's move forward. Let's make it, so this is where things start to kind of ramp up. We still have like 15 problems left, and now we have the word problem bases of these, so probably still a ways to go. How long have we gone so far? About an hour. All right, making an argument. You friend, typo. We got a typo, guys. I wonder if this is an old digital version, though. I got to check the copies of the book that I have. Your friend claims that if the radius of a sphere is doubled, then the surface area of a sphere will also be doubled. Is your friend correct? Explain your reasoning. Well, I'm about to sneeze, maybe. So, your friend would be incorrect. We have learned that areas, you square your similarity ratio thing. So, you friend is incorrect. I'm intentionally saying you. For those who are only watching this and have me on mute, Mr. Robinson, you said you, not your. Well, look at the book. Look at the book. All right. Your friend is incorrect, or you friend is incorrect. Doubling, if the similarity ratio, if you double the radius, I'll say scale factor as the book would. The scale factor is 2, and therefore any area, including surface area, ratios will be squared that scale factor. So 2 squared is 4. Therefore, your surface area would be quadrupled. Quadrupled. Okay. That's it. You can check. Now, here's the thing. You can check. 4/3 pi, and then you do the squared thing, right? I can show mathematically. But you'd be squaring the 2, the r that's doubling, so you'd be squaring the 2, you'd get 4. All right, modeling with mathematics. The circumference of Earth is about 24,900 miles. I think we learned something about the circumference of the Earth based off of that guy. I forget his name. Some Greek guy. Find the surface area of the western hemisphere of the Earth. So if I have a circumference of 24900 miles, and I want to use the radius for surface area, I'm going to set 24900 equal to 2 pi times the radius, and I'll divide by 2 pi, and I'll get a radius here. I'm going to go ahead and divide 24900 by 2, 24,900. 24900 divided by 2. And I get 12,450, 12,450 over pi. So this is the radius in miles of the Earth. Probably about 4,000 miles when you divide by pi. Probably about 4,000 miles. Now, let's find the surface area of the western hemisphere, of a hemisphere. So a surface area, the core is not included, right? There's no base area thing here, so we will just use 2 pi r squared. So 2 pi times this radius squared should give us the number that we're looking for here. So 2 pi times 12,12450 over pi squared will give me, a big number. This is approximated, by the way. I'm not writing the exact one right now. 986776656. Do they say rounding? 0.27 square miles. And that's just, is that right? That's just a hemisphere. That's just a hemisphere, y'all. So, yeah, nice big old number. A lot of square miles of coverage of Earth. Remember, this isn't miles, but square miles. But quite a bit of them. Feeling pretty small right now. What is that number? Here, hold on. Let me include commas. 98 million. 98.6 million, or 0.7 if you want to kick it up a little. Just kind of round it that way. Square miles of Western Hemisphere. Okay, let's go to number 35, modeling with mathematics. A silo has the dimensions shown. I thought it was the Leaning Tower of Pisa for a second. The top of the silo is a hemispherical shape. Find the volume of the silo. How much stuff can you fit inside of it, basically? Okay, so I have a diameter, basically, of 20 feet. That's what we're looking at right there on the bottom. Looks like a diameter, so that's kind of a radius that we can discover. So radius will be 10 feet, half of that. And the height is 60 feet. Now, the radius applies also to the hemisphere up top. That's kind of the guess there. So if the radius is that, we have like an object 1 and an object 2. Now, so the height is just for object 2. As far as the volume of object 1, we'll do 2/3. It's a hemisphere. 2/3 pi times 10 squared. I think we've seen this a lot. Oh, not for this one. 100 times 2 is 200. So you get 200 pi over 3. That's in square feet. Oh, we need volume. Pi r cubed. I confused two things for a second. So 2,000 pi over 3. I think we've seen this a lot. Cubic feet. There we go. Don't mess this up, Mr. Robinson. Do not mess this up. So there's volume 1. Volume 2 It's one of those things where if I wasn't recording and doing this stuff, if I was doing it on my own piece of paper or whiteboard, I would never mess that up. It's because I'm trying to say things out loud. Volume 2, we do area of base times height. Let's just write that all in as 1. We do pi times the radius squared times that height. 100 times 60 is 6,000. So you get 6,000 pi cubic feet here. So the volume of the total, I don't know if anyone cares about all whole numbers anymore, or the exact answers, but we get 6,000 pi plus 2,000 pi over 3. Common denominator means we would need to get 3 over 3 here, so we get 18,000. Let's move it over here. 18,000 pi over 3. So we get 20,000 pi over 3 cubic feet of silo stuff. So more than 20,000 will be the answer, cubic feet. So 2,0,0,0 pi divided by 3. 20943.95. 20943.95. So we added the hemisphere's volume with the cylinder's volume. That's in cubic feet, assuming every other math part that I had before typing that last part in the calculator held up and was accurate, then we should be good. Okay, let's move forward to number 36, modeling with mathematics. 3 tennis balls are stored in a cylindrical container with a height of 8 inches, probably for the whole container, and a radius of 1.43 inches. The circumference of a tennis ball is 8 inches. So let's do here. Because once they said circumference, I was going to ask, are we kind of making up and assuming the tennis ball's radius is the same as the cylinder's? Because it shouldn't maybe be exactly the same. Maybe not. Find the volume of a tennis ball. Find the amount of space within the cylinder not taken up by the tennis balls. So yeah, it is kind of interesting that they give you a radius of the cylinder and it won't apply to the tennis balls. I mean, I call that real world because this cylinder should be a little bit thicker than that. So this thing here is 1.43 inches, but the tennis ball will kind of have its own radius. I'm going to give it its own R. It doesn't happen to be 1.43, maybe because it sits inside the container a little bit. Maybe there's some air, maybe there's some jostling, and it's just smaller. So when it comes to the tennis balls themselves, we don't need, all we need is the circumference part. So the circumference, what number is this, 36? The circumference of the ball is 8. 8 is the same as 2 pi times the tennis ball's radius. You divide by 2 pi, you get a radius of 4 over pi inches. That's the radius of the tennis ball. Maybe not exactly 1.43. You want to know what 4 over pi is? It's got to be either equal to or less than. 4 over pi, 1.27. So it's not the same radius. Now, I'm not going to round just yet. What do we want to do next? We want to find the volume of a tennis ball. So the volume of a tennis ball, of one of them, is 4/3 pi times that radius cubed. Now, I still have my other calculator thing where I can enter things into that equation, into the table, I should say, with the equation. I have the surface area portion, which I'm not going to use. Whoops, I started typing the wrong thing. Clear. 4 over pi. I started typing the whole formula when I totally didn't need to. And I'm getting 8.65, about 8.65 cubic inches. Now, remember that this is a rounded answer and there are 3 tennis balls total, so I'm going to use the exact answer that's provided later. I almost feel like I should now write an exact answer because I'm going to use it 3 times. How about this? This is an answer for one of the parts. This is part A. This is part A. Part B, I'm going to tell you what 3 tennis balls volumes are because we are going to use that. They say find the amount of space not taken up by tennis balls. So I'm going to go ahead and take that previous answer and I'm going to triple it. So, I don't know how to copy paste it. Maybe I can't. Okay, I guess I got to type it in. So sorry, 4/3 pi times 4 over pi cubed. Okay, that wasn't too long. And then times 3. Okay, tripling it, I get around, because I'm not writing exact numbers, 25.94 cubic inches. I will be using exact answers in my calculator though. So the volume of the cylinder, let's find that. The volume of the cylinder is based off area of base times height. Now the area of base is pi times its radius, 1.43 squared, times the height of this thing, and they said the height of this is 8 inches. So I'm going to write the exact version of that one. 1.43 squared times 8 is 16.3592 pi, and that is also in cubic inches. So volume of that one is that, and the 3 volumes of the balls are this. That's a rounded value. So the volume of the air inside of there is going to be 16.3592 pi minus whatever I have in the calculator for this exact value, or for the 25.94. So I'm going to multiply that thing by pi, and then subtract this other answer that I had, and I didn't save it. Hold on. Shoot. Oh boy. I need to get the previous answers out. Give me 1 second, guys. 16.3592 pi. Okay, I'm getting 25.46 cubic inches. It's not a mistake. Wow, that's actually a lot of air compared to that, because it's like there's just as much air as there are tennis balls. So I didn't really expect that. I expected it to be like pretty airtight, but I guess there's just space. I guess that's just how it works. There's that much air. So I'm gonna go with it. I'm gonna say that seems reasonable with respect to what we're doing in the picture and stuff. So let's use it. I didn't box this answer for A, by the way. All right. So let's move on to number 37. Use the table shown for a sphere. Find the surface area and volume. Okay, I still have that other formula thing, so I'm going to go ahead and show you it. Let's go to the table, and let's clear out all these other ones. Give me 1 moment, y'all. I'm going to delete. Okay, let's go to my calculator. And if I just type in these numbers, if you saw in the thing, I need 6, 9, and 12. Let's confirm that 3... Oh, these are in terms of pi. Then let's do this. Let me take pi out of my equations, because then when I don't multiply, I'll write pi in my answers. And let's just confirm this thing works. The first numbers they had here was 3, and they have 36 pi and 36 pi for those answers. They happen to be the exact same volumes, which is just surface area and volume were the exact same number, which is coincidence. One is square inches, one is cubic inches. Anyway, let's see that we get the number 36 by plugging 3 into this equation thing here. Just confirm that it's working. Okay, it's working. So I'm going to plug in 6, 9, and 12. And these are the answers we'll have in terms of pi in this table. Okay, so it says use the table shown, copy, and complete the table. I'm going to do that right now off screen while you're not looking. Look over here, 37. I copied the table, and I'm going to write these numbers in and include a pi and those units. I'll do it after right now. Okay, what are my numbers? We have 144 pi square inches, and then I'm going down. 324 pi square inches for surface area for 9 inches, and 576 pi square inches for that one. So this is what I have so far, those three. Now I'm going to write the volumes. The volumes say 288, and I'm going to write pi, cubic inches, 972 pi cubic inches, and 2,304 pi cubic inches. So they're all in terms of pi when it comes to answers on there. All right, that's part A. Part B. What happens to the surface area of the sphere when the radius is doubled, tripled, quadrupled? This is it doubling, right? That's times 2, and here's times 3, etc. So what happens to these things here? This is doubling, and this gets quadrupled. 36 times 4 is 144. We triple it, suddenly you do 36 times 9. You quadruple it, suddenly this is 36 times probably 16, because you got to square whatever number it is you're talking about. So what happens to the surface area? It becomes the square of that scale factor. It becomes the square of that scale factor. So when it's doubled, you do times 4. on the surface area, etc. When it's tripled, you do times 9. What happens to the volume of the sphere when it's doubled, tripled, quadrupled? So these things, once again, it becomes the cube. This one, when you double here, this number here is 36 times 8. That's 2 cubed. When you triple, this is 36 times 27. That's 3 cubed. I mean, I just know that that's how those things work. So I'm telling you it right now, and you can go and try and multiply, and that's what happens. So it becomes the cube. So I think I'm going to write those in this table of that scale factor. Sorry for the handwriting. That's why I generally type these. So here we have times 2, times 3, times 4. And here we have times 4, times 9, times 16. And here we have times 8, times 27, and times 8, times 27, and times 64. That's 4 cubed. 36 times 64 is 2304, and the pi still remains within there. Okay, number 38. Still 10 questions to go. It actually is taking up some time here. We're probably still going to have, we'll see if we finish within the 2-hour mark. Mathematical connections. A sphere has a diameter of 4 times x plus 3 centimeters and a surface area of 784 pi square centimeters. Find the value of x. Well, let's start with the diameter portion. The radius will be half of that. Just divide the 4 by 2, and you get 2 times x plus 3. Right? So surface area is 4 pi r squared. Let's substitute into here, and we get 784 pi equals 4 pi times 2 times x plus 3 is about to be squared. It's about to be squared. Give me one moment. Okay. First thing I'm going to do here, actually, I'm going to divide both sides by 4 pi. I'm not going to dare try and distribute that stuff in there. So divide by 4 pi, get the pi's out of there completely. 784 divided by 4, I don't know. I can guess. Oh, 196? Okay, 7. Whoops, I'm not in the mode. 784 divided by 4. 196. Okay. So 196 equals, now here's the other part. I'm going to square both of these. This is 4 times x plus 3 quantity squared, but I don't have, see, I just squared the 2. And I'm still squaring x plus 3, but I don't have to distribute that thing unless I feel I have to. If I divide everything by 4 now, that would be incredibly helpful. Let's actually write the x plus 3 squared on this side. X plus 3 quantity squared, and 96 divided by 4 is 49. So I can take this, I can solve using square roots. I can take the square root of both sides here. So x plus 3 equals, now I'm going to start with algebra here, plus or minus, excuse me, I'm going to start with the concept of not physical lengths of things. It says find the value of x. I'm just going to make sure that both things are accounted for just in case the negative answer can qualify. So I subtract 3 from both sides. I get x equals negative 3 plus or minus 7. Oops. Plus or minus 7. And negative 3 minus 7, negative 3 plus 7 is 4. Negative 3 minus 7 is negative 10. So those are the two different answers here. But because the diameter is 4 times x plus 3 and the radius is 2 times x plus 3 and things like that, negative 10 can't apply to this. Negative 10 would give you a negative result, and we can't do that. 4 should be fine. 2 times 4 plus 3, that's 14. And 4 times 4 plus 3 is 28. And that should probably give you that surface area answer. So I'm going to trust that x equals 4 is the one that we needed, and we're all good. Okay, let's move forward into number 39. Modeling with mathematics, we have the radius of the Earth is about 3,960 miles. Remember when I said about 4,000? So there we go. On point, radius equals 3,960 miles. The radius of the moon, radius Earth and radius moon is about 1,080 miles. That's actually a pretty good size. Okay. I didn't realize it was go moon. Find the surface area of the Earth and the moon. SA for Earth is 4 pi times r squared, and surface area moon is 4 pi r 1080 squared. I still have my calculator thing to use, so I can. Hey, this is Sam. I wonder if I should just use that calculator thing, go with it, because I don't know. I'll write the ones in terms of pi first. I don't know if they're going to do it. I'm going to go to the calculator. So I'm going to type 3960 as a radius, and I get, oh, never mind. My calculator does a weird thing here where it has this scientific notation. I'll leave it. I'll do it in the main. Oh, this isn't in terms of pi yet. The numbers will be big anyway, but you know what? That's the exact answer without pi, right? We removed it. So, okay, I'll go and use these. So this is 6272640 pi. And of the moon, it's... I got to move over. Oh, that's volume. Hold on. That's not the moon. That's volume of the thing. 1080. For the moon, it's 4665600 pi. Okay, so I'll let the rest I'll do the rest on my own. So square miles. Okay, that's the exact ones. Let's leave it like that for a brief moment in time. They said compare the surface areas of the Earth and the moon. That means we have to do a division. So let's do Earth over moon in that case. Surface area of Earth over surface area of moon. So we'll do 6272640 pi over 4665600 pi. Pi's will cancel, and let's see what that number kind of works out to be. So 6272640 divided by 4665600, and I'm getting 13.4 repeating. That should be 13 4/9, which should be 121 over 9. Let me see if that's right. Math, fraction. 121 over 9. So it equals 121 over 9 exactly as far as a ratio goes. These are all approximated to begin with. So that's the thing here when it compares. That's the ratio of the surface areas of those two. It's just the ratio. It's just how it works. That was parts A, B. Part C says about 70% of the surface of Earth is water. How many square miles of water are on Earth's surface? You just got to multiply your Earth's surface area by 0.7. So we'll take 6272640 pi. This time I'm going to actually use that pi in my answer. So 0.7 times 6272640 pi. Not use pi in my answer, but I'm going to actually calculate with pi involved. So this is going to be 137942558.2. That's all I got as a number, so I'll just take that off. Square miles of water, of not of water, of water on the surface, if that makes sense. So when it says that much of the world's covered by water, it's from what you see from space or whatever. Obviously, it goes within there. We're not in a drought. We don't have trouble here. Come on, here we go. All right, number 40. The torrid zone on Earth is the area between the Tropic of Cancer and Tropic of Capricorn. Tropic of Cancer is a line above the equator, Tropic of Capricorn down here. The distance between these two tropics is about 3250 miles. You can estimate the distance as the height of a cylindrical belt around Earth at the equator. Estimate the surface area of the torrid zone. The radius of Earth is 30.6 miles. Well, a cylinder, it's not truly, because if it were a cylinder, then, cylinder is kind of a flat, concept right here, like that. But the Earth bulges, so they did say estimate, so estimate, I suppose we will. So if this is your torrid zone, we have a radius Wait. Do we use the radius? Oh, it's right down here, 3960. I was going to say, should I just use the one from above? But what if someone didn't see that problem? So 3960 miles, and then this is 3250 miles. Clearly not drawn to scale. But that's that stuff. Now, when it comes to torrid zone, we are not including the top and bottom surfaces. It's just this lateral facing right here. This is something where I guess you would have to understand the concept of this unfolding of this torrid zone here. So this circumference matters because if I cut the torrid zone open, if this was a can of soup and I cut off the label and unfolded it, you'd be basically looking at a large rectangle. And this large rectangle is now the torrid zone, where this portion is the circumference of your circle, the top base or the bottom base. This is circumference, which is 2 pi times this radius of 3960. This is this flat part here, and then the height is still 3250. The reason why you want to do this for surface area, this is miles, the reason you want to do this is because flattening it out is an area, the same way we unfolded the party hat of the cone to get a flat version of it and find its area using other means. This is a rectangle. And I can find the area of a rectangle, and yes, I'll multiply this. This is 7920, so 7920 pi miles for that circumference. So we have this times this base times height to work off of, and that'll be our torrid zone's surface area. So surface area of torrid zone is going to equal 7920 pi times 3250, and this will be a square miles answer. This is going to be big. This is going to be somewhere in the like hundreds of millions of something. So 7920, and I hope that 3960 doubled is that number. I think it is. Pi times 3250, and I'm just going to write out the number. 808,64594.9. I don't know if that part's going to matter. Square miles, and that is including multiplying pi with that portion there. So as a whole, right, is this thing quite accurate as far as, let's see how to say what I'm trying to say. Is this thing very accurate? Well, remember, the Earth bulges more so than this, so we're kind of doing what we can when it comes to that, but it's close enough to what we need because getting a portion of a sphere isn't quite as easy as it sounds. There's a lot of calculus involved in that. Even for a circle, it's not as easy. It's like trying to find just this area of a pizza if you cut it into this part and there's a circle. It's not very easy to do. But with that, or at least not in this way, not unless there was an angle from the center. But with that in mind, we got something. It's about 80.9 million miles. And that was part A. That's discovery. That's part of the cylinder's surface area. When you do those things, I know you haven't learned it, but what you do is multiply 2 pi r by the height of the cylinder. We didn't add the two base areas. Part B. A meteorite is equally likely to hit anywhere on Earth. Estimate the probability a meteorite will land in the torrid zone. Okay, just so you know, when it comes to this answer, this is assuming it's going to hit the Earth. This isn't the probability that this will hit this part of the Earth in general compared to anyway. It's like throwing the thing at the dartboard. Okay, anyway. You take your surface area of this and divide by the surface area of the Earth. Did we get surface area of the Earth in this problem? Yes, we did. So I'm going to take this number. Oh, let's get the exact ones. Do I have the exact one for this? I do. I'm going to delete some stuff here. But surface area of Earth is that guy. I never did write square miles, but that's in square miles. This guy here, let me do 7920. 7920 times 3250, just to get it in terms of pi. So this other one, the torrid zone, which I probably could have written above, but now I actually got to use it. 257.40000 pi square miles. So that's in terms of pi. So I'm going to divide this by the surface area of the entire Earth. Okay, so probability of meteor on torrid zone, TZ, will equal 257.40000 pi over 6272.6400 pi. It's actually quite a bit of the Earth. It's more than a third of it, man. That's a lot of it. So let's divide that by the other 6272.6400. 6400. We're getting 0.41035. 0.41035, about a 41% chance. That torrid zone's covering quite a bit of the Earth. You have to understand that when it comes to the torrid zone, you go like, how is this 40% of the entire Earth? You have to understand this is the largest part of the Earth. This is part where the Great Circle is. It shrinks up at the top and bottom so much so that this is about 40% of the Earth. Almost makes sense for that stuff, covering it. So that's what I'm going to say, about 41% based on calculating that there. That is part B for number 40. All right, number 41. Still 7 problems to go, I believe. Abstract reasoning. A sphere is inscribed in a cube with a volume of 64 cubic inches. What is the surface area of the sphere? Explain your reasoning. Well, I'm going to explain through math, and I'll explain in words out loud. I probably won't type it. So if I have a cube, oh my gosh, that's terrible. That's the worst cube I've ever drawn. If I have a cube and I don't even know how to draw a sphere inside of here, but if it's inscribed inside here, then it's kind of hitting all parts of it. The point is, that's a terrible drawing. The other point of this thing is that whatever the cube's edges are, they're all the same. So when you multiply them all, you should get the 64. Take the cube root of both sides here, and the cube root of 64 is 4. So each length of the cube is 4 inches. So 4-inch cube, which means the sphere also has a diameter of 4 inches. The diameter is 4 inches because if this goes 4 across right there and it's inscribed inside it, that's what we get. The diameter is 4, therefore the radius is 2, therefore I can find its surface area. The surface area is 4 pi r squared, which is 16 pi, and we've seen that number before. That is, what was it? I don't remember, so I got to calculate it. 49 point something. 16 pi. That was earlier on. That was a couple of hours ago. 50.27. 50.27 square inches. Unless they want to do it in terms of pi. That's what we're going to get. My justification is based off my math. Number 42, how do you see it? The formula for the volume of a hemisphere and a cone are shown. If each solid has the same radius and r equals h, which solid will have a greater volume? Explain your reasoning. It looks like the hemisphere would have a greater volume, and I'm going to assume that it does, but they probably want something mathematical. See, understand that if r is h, then this could also represent h the same way that the other one does, like that. So, or better yet, I can turn this one into r. If I turn this one into r here, then the volume of the hemisphere is still 2/3 pi r cubed, but I can say the volume of the cone as 1/3 pi r squared times r. And that means that's 1/3 pi times r cubed. So we're comparing 2/3 pi r cubed versus 1/3 pi r cubed. And 2/3 pi r cubed is twice as big. It's not only bigger, but it's literally twice as big. So which solid will have the greater volume? The hemisphere. The hemisphere. Explain my reasoning once again. It's shown in my math, but hemisphere, and it will be twice as big. Have twice as large a volume in this particular instance. The particular instance is that the radius and the height of the cone are the exact same. Which, I mean, it makes sense that you can kind of fit that cone inside there, right? It kind of touches the bottom and does that stuff. So there's also a logical reasoning to that I'm sure we could do. All right, 5 more problems. They're probably the longest ones. Let's see. Critical thinking. Oh, yeah, probably. Number 43. Let V be the volume of a sphere, S be the surface area of the sphere, and R be the radius of the sphere. Write an equation for V in terms of R and S. Hint, start with the ratio V over S. Write the equation for V. Okay, start with V over S. So V over S. And I like to write SA just because I can do that. So volume, oh, I get it, because you have a cubed part on top and a squared part on bottom, and you'll have R in it. So volume is 4/3 pi R cubed. Surface area is 4 pi r squared. Maybe they don't want pi in the answer. Maybe that's a part of it as well. So these cancel. The 4's actually cancel, and if you're not sure how this 4/3 works on top, it's the same thing as just having the 4 on top. Have the 4 on top here, and then you divide by 3 on bottom, which multiplies by that 4. But this is nice because these 4's also cancel. They divide out. And the r's, there's an r cubed right here and an r squared. Both r's can cancel out here. If just 2 of them cancel out here and you're left with r. All we have now, volume over surface area, I'm going to put S. I'm not going to be stingy like that. Volume over surface area equals, I have an r on top and I have 3 on bottom. I didn't know this. So write equation for volume in terms of r and s, multiply both sides by s. The volume is r over 3 times s. There's got to be a better way I can write that. And by the way, that is an s, that's not a 5. Maybe that's better. Why write surface area? So I don't know what version they could write. They could write 1/3 s times r. They could have a bunch of different things there. If I do alphabetically, I do the 1/3. So I'd say volume is 1/3 lowercase r and capital S, like that. 1/3 rs. Now, to say I didn't know that formula is true. To say that we couldn't have discovered, because I was thinking when we were doing those other problems, when I was using the table, I was thinking, why don't I just use a formula to go from one to the other? And this totally makes sense to do that. I get what they mean now. They don't want any pi in the answer. They don't want r to be squared or anything like that, if they don't have to. And there it is. Or there it should be, I should say. I'm only assuming my answers are correct. It's my first time seeing these problems. Number 44. Thought-provoking. I've seen thought-provoking before with frustums. This better not be a frustum. A spherical loon, I don't know what that is the region between 2 great circles of a sphere. Find the formula for the area of a loon. So is it only on this side of the sphere, though? Is it just on the front? It looks like it. So you have a radius of r. Okay, here's how I imagine it. They give you a theta. So if theta is an angle that we can use on this, I'm thinking of this the same way you'd find the area of a sector. Remember, in the area of a sector, you have the center, because we're clearly from the center, they're talking about r. If I had this r and this theta and stuff like that, I could find the area of the sector by taking a portion, a fraction, out of 360, because theta still rotates to 360 no matter what. Whatever theta is over 360, the area of the sector, x, I'll call it, x is out of the area of the entire circle, pi r squared. Let's use that concept, but for the sphere. So for the sphere, we do the spherical loon. We could say whatever fraction we have out of 360, whatever theta is out of 360, this x, I'll call this x as well. Whatever theta is out of 360, this x is out of the surface area of the sphere, so 4 pi r squared. It's like the same thing. The only thing, though, is I don't know if they're going to do 360 for these things. I feel like this would be a radian measure thing, because we probably don't rotate. I'm going to guess they use radians for this kind of thing, not 360. So I'm going to use, in terms of radians, 2 pi is the radian equivalent of a full circle. Radians. So let's multiply both sides by 4 pi r squared and solve for x. 4 pi r squared. You'll notice that the pi's cancel. No, r's cancel there. And 4 divided by 2 is 2. So you're left with 2 r squared times theta? Oh. This isn't just 2 pi. This would be 2 pi r, because this isn't necessarily a unit circle. So a set of r's would cancel, and you'd have 2r like that. So 2r times theta is x, and that would be spherical loon. That's only if we're in radians. I mean, they didn't bring up that this thing would be in radians for that thing, but I feel like that's just going to work out that way. No, 2 pi is still the radian measure. I don't think we'll use r there. So, yeah, 2 pi is still a radian measure. This isn't about circumference distance. 2 pi is a radian measure. I should know better than that. So I'll say 2r squared times theta will be that one. This is area of, I'll just call it a loon. The area of the old loon there. I'm working off that. That's assuming we're in radians, right? Assuming we're in radians. Radians. Okay. If you did 360, it would be different. See, I started thinking about radians because I wanted the pi's to cancel. I didn't want a bunch of things to go out here, and I think that this worked out better. All right, number 45. 45, 46, 47. We're still on the last page, or we are on the last page. The volume of a right cylinder is the same as the volume of a sphere. Okay, so 45. I'm already thinking in terms of that. Volume cylinder equals volume sphere. So I'm already thinking of area of base times height, pi r squared times height equals 4/3 pi r cubed. The radius of the sphere is 1 inch. Give 3 possibilities for dimensions of the cylinder. Oh, these might be different radii. So this, I totally didn't realize that this radius of the cylinder, radius of the sphere, they have the same volume. That doesn't mean they have to have the same radius. If they did, then they might not be the same volume. So if the radius of the sphere is 1 inch, r sub s equals 1. Now I have an equation that says pi r sub c squared times height equals, you know what, this time now we only have a single r here. I'm just going to leave it as r. Equals 4/3 pi times 1 cubed is 1, and 4/3 times that is just that. So what do they want? 3 possibles for the dimensions of the cylinder. Okay, let's cancel out the pi's. R squared times h is 4/3. Let's rewrite it so that we do... Let's just get something by itself. Let's get height by itself and divide by r squared. I can say height equals 4 over 3r squared. So now I can substitute values for r, and then I'll get values for h as a result. And I actually would rather use the calculator to try and get whole numbers on here. I think as long as I get numbers that divide by 3, well, I won't get full whole numbers no matter what I do. So let's just plug in some numbers here. It's like a table. Let's use r and h. This is an open-ended question, I think. It says give 3 possible values. So they need to be positive. So if r was 1, oh, we can't use 1. If r was 2, 2 squared would be 4. 4 times, oh, and 4 over 4 is 1. You'd get 1/3. You get a height of 1/3. If r was, let's say 1/3. If r was 1/3, 1/3 squared is 1/9. 3 divided by 1/9 is 1/3. And 3 times 1/9 is 1/3. And 4 divided by 1/3 is 12. Are there units to these? Inches? So I'll do these later. And then if r is, let's do 1/2. If r is 1/2, 1/2 squared is 1/4. Oh, that'd be a weird fraction. I want to do, I don't know, let's just do 3. Yeah, let's do 4. If radius is 4, it'll be a small height, by the way. We'll do 4 squared is 16. 4 divided by 16 is 1/4, and 1/4, the 3 times 4 multiplies, you'll get 1/12 here. So these are just different numbers of these things. I don't really know what else to say. So we can get a radius of 2 inches and a height. I'm going to write these out. R equals 2 inches. H equals 1/3 of an inch. Or radius is 1/3 of an inch and the height is 12 inches. This is a cylinder, right? Yeah. Or the radius is 4 inches and the height is 1/12 of an inch. I don't know. Assuming that I got this thing by itself properly and it's kind of open-ended, plugging in numbers for one versus the other, then I think anything can really apply in that way. And you're all good, right? You can just plug in any different numbers and you're good to go. So I got just a couple there and looking good. Okay, Oh, maybe I could have plugged in 1 because they only plugged in 1 for this one. And if I did plug in 1, I would have gotten what? 4/3. So we're all good. All right, so those are a few of them. I got a couple more questions here. Number 46, problem solving. A spherical cap is a portion of the sphere cut off by a plane. The formula for the volume of a spherical cap is that. I feel like I almost got to write that. Where A is the radius of the base of the cap. Okay, the cap is the top. The base of the cap, and H is the height of the cap. Okay, it's kind of intimidating. Use the diagram and given information to find the volume of each spherical cap. Radius is 5, A is 4. Find the what? Volume? How do I find? Oh, they give you the formula. Duh. I was say, how do you find the? All right, I got to box that. Otherwise, I'm going to forget that I can use it. Let me actually probably write it down. But that's what I'm highlighting. This is number 46. So the volume of this guy is pi h. And I don't know how this is. I'm sure calculus gets you all this. I'm not sure how they come up with this stuff. Squared. So I need A and H for my volume. Those are my only variables in here. And I'm assuming they're going to have us round these answers. I probably would want to do it given all that we have here. So I need A and H. So I need to use R somehow to get H. Obviously, use A as well. So I have a right triangle in this scenario. And this radius can also be applied here, right? This would also be radius, which means this length here, X, well, I don't want to call it X. Let's just, if this is R and this is H, then this here is R minus H. So, Pythagorean theorem, well, I don't need to use, let's just use Pythagorean theorem to find out that length, and then I'll take whatever radius that I have to find H, instead of making it too overcomplicated there. For now, let's just use Pythagorean theorem. So for part A, if R is 5 feet and A is 4 feet, then I can say in Pythagorean theorem that my, you know what, I will call it X. I'll call this X, and I'm going to say that X equals R minus H. So I can set it up here. X squared plus A squared equals R squared. This is going to be a 3, 4, 5 triangle. And this is going to be 3. So X is 3, as if to say R minus H equals 3. Now, R in my problem is 5. So 5 minus H is 3. Well, H is 2, right? 5 minus what is 3? Your height is 2. So you get a height of 2 feet. So I have A of 4 and H of 2 I have to use in this formula, with the 46 involved as well. I'm going to erase the 46. So I have to do this 4 times. A was what? 4. So my volume will be pi times 2 over 6 times 3 times 4 quantity squared plus 2 squared. I could go to the calculator here, but I'm going to work out some of this. This is pi over 3, and this is 1648 plus 4. So this is 52 pi over 3. 52 pi over 3. This is square feet. That's an exact answer, but the rounded answer, this is just for part A. The rounded answer, I haven't used the calculator in a while, it turned off. 52 pi over 3 is 54.45. 54.45 cubic feet, not square feet. I apologize. Cubic feet of that guy. 54.45. Okay, let's go to part B, where I have 34 centimeters and 30 centimeters. To be fair to myself, and I'm going to, these look to mostly be Pythagorean triples. So instead of using a big part of Pythagorean theorem, I can encourage you to use it while I tell you what these numbers are, and I'll say what I know out loud. There's a benefit to knowing Pythagorean triples, and I'm going to be a beneficiary of that information. So R is still the hypotenuse, where A is that other guy. So the X that we're talking about, as far as X squared plus this squared equals that squared, this is part of a 8, 15, 17 Pythagorean triple. So if this is doubled and doubled, 8 doubled is 16. So you get 16 centimeters. Part of the 8, 15, 17. You can work it out, but that's what we'll get. So that is, what did we say? R minus h. X is r minus h. So 34. 34 minus what is 16? 18. So you get a height of 18 centimeters. So we'll use A is 30, H is 18, and we'll plug it into that thing there. So volume is pi times 18 over 6. That looks like 3 pi. 3 times A squared, they gave us nice big numbers, plus 18 squared. So again, 18 over 6 is 3, so you get 3 pi times, that's 900 times 3, 2700, plus 324. Or 3, I gotta calculate that. So this is 9,072 pi, excuse me, square cubic centimeters, which is about, times pi, which is about 28,500.53. 28500.53. I feel like that's like, hey, that's the right answer because it was so close to 28,500. Maybe. No idea, but it sounds good. It's like that's the number that they intended to get, you know, kind of like that. Okay, let's go to part C. There are 4. They should have just done this with 2 of these. Part C. 13 meters and h is 8. You know what? This one's not a Pythagorean triple. I thought this was the 5, 12, 13 one. So, okay, this is not going to be as good. This time we need to find A. No. And, oh, actually, maybe it can be part of the Pythagorean triple. This one's a little interesting because that's H. So, R minus H will give us that other value. So this is part of the Pythagorean triple. R minus H is that X value, right? So 13 minus 8 is 5 equals X equals 5. Okay, I'm going to use that to find A. So that's 5 squared plus A squared equals R squared. This is a 5, 12, 13 Pythagorean triple, so A is 12. So they are Pythagorean triples. So A is 12, H is 8. Let's use that formula again. I have volume equals pi times 8 over 6. Not much of a reduction, but it is one. 3 times 12 squared plus 8 squared. So that's 4/3 pi, 4 pi over 3, times 144 times 3, 432. Yet I wrote a 3. 432 plus 64. Let's kind of work some parts out with that. So 432 plus 64 is 496 times 4 is 1984. Now 1984 I don't believe divides by 3. So I'll write that as 1984 pi divided by 3 cubic meters. And that rounds to, I waste a lot of space in writing this stuff out. I really wish I just wrote them on single lines. So times pi divided by 3, and I get 2077.64, 2077.64 cubic meters. So as long as I got the right A, which I fully believe I got the right A using the Pythagorean triple stuff, right? As long as the formula is good and I got all that, it's good. Trust a calculator. Part D. Will we finish in the 2-hour mark, by the way? No, I don't think we will. Part D, 75-inch radius. I was correct in that I thought that 2 hours would be a stretch for the last 15 or so questions. And height is 54 inches. So X is still that R minus H, right, that I'm using. So X is R minus H, which is 21 inches. So this is a 21 squared plus A squared equals 75 squared. And guys, this is a 7, 24, 25 Pythagorean triple. You know how you can see the 7 tripled, 25 tripled. What's 24 tripled? 72. A is 72. I'm saving myself time. So I have H of 54, A of 72. Big numbers. I barely saved time because now I got to work off this part. Let's try and shrink these into one line each. V is pi times, where's h? 54? Pi times 54 over 6 times 3 times 72 squared plus 54 squared. Who are they? The thing is, I don't know how many of you guys watched till this part of the video. Maybe you fall asleep to me and you wake up and go, I'm here. But how many people are doing these problems from this stuff? You're like, I'm Mr. Robinson, I'm watching and I'm learning off this stuff. So basically, who are they tormenting? So the question I was going to say while I start to compute what this is, who else are they tormenting besides myself? If I'm the only one doing the problems and I'm speaking to myself and no one else engages in this part of the video, I'm the one who's being tortured through this. The problem writers are like, we'll just write big numbers. We won't even do the problems ourselves. We'll make photomath get answers or whatever can get these answers. I don't know what can get these answers. This plus 1550 2 and then times 9. This is going to be a big number. So this is the number just in terms of pi. 166,212 pi. And this is square cubic inches. And so that rounds to times pi. 522,170.40 cubic inches for the last guy. And these are spherical caps or whatever they called them. And I'm glad that I don't have to see them again unless it comes in some sort of review or something. Okay, last question, number 47, critical thinking. Yeah. A sphere with a radius of 2 inches is inscribed in a right cone with a height of 6 inches. Find the surface area and the volume of the cone. If it's inscribed in it, it means that it's touching it at every which point, right? So you would need the radius. Well, you have. Oh. Well, okay, I'm bad at drawing spheres. I mean, if they said draw a sphere, I don't even know how to, I'm bad at like getting the idea. Like, okay, here's my 3D sphere, okay? But this is inside of a cone. It's inscribed in a cone. So it's like hitting this side of the cone and hitting this side of the cone and also technically hitting the bottom of the cone. And the idea, and the problem is the cone's in 3D. So it's kind of hard to show how the bottom is, except that like, boom, it's hitting at that center. But it's hitting like here and here and there. And these parts are above, if I call it the great circle, these parts are above the great circle because the cone's slanted, right? It has to hit it tangentially. So I have to figure out like what are we finding? Where are we? Oh, surface area and volume of the cone. So I need the height of the cone surface area. I need slant height. Oh, I have the height of the cone. What is it? 6 inches. So I have the height of the cone. I can probably find the volume because we have the radius. No, we have the radius of the circle, of the sphere. Well, we do have the radius of the sphere, right? It's 2 inches. So if that's 2 inches, then this is 2 inches down, 2 inches up, which means this has 2 inches to spare right there because the whole height of this is 6 inches. This is kind of a lot being drawn in there. How does that help me? What I want to do is figure out, oh, here's the other thing. If it touches tangentially, these will be right angles. So I could, okay, this is in 2D, but this is in 3D, but what I could do is give you the 2D equivalent, right? Let's look in the cross section of this whole thing. And I pretty much drew what I wanted to draw, but let's do it again with like nice clean shapes. So I think I'm getting an idea of what I can do, at least for slant height. I just got to think of the angles of this thing. I can use trig for that if I have to. Let me draw the circle first. So I'm going to draw like a 2D representation of this. It should still plan out to be exactly what we're talking about. So I got some center. Oh, no, it just keeps disappearing. I got some center of this here sphere. Okay. And I will draw a triangle around it. Pretend like though this is the sphere and the other thing that we do is the cone. Okay, so let's do a cone, but it has to touch things tangentially. So it's got to be like, I got to kind of squeeze it in to make it kind of right. So kind of like that, right? We have a, sure, that's perfect enough. That's actually not bad after many tweaks. So the cone, that's now a triangle, the cone has a height of 6 inches. Okay. Maybe the center's off. Maybe that's what's throwing me off right now, because I was trying to fit everything around this, and it doesn't look like the center's quite centering. There we go. So this height is 6 inches. Now what I care more about is the fact that since this is 2 inches and this is 2 inches, then this has to be 2 inches. That's what gives you 6. Now there are points of tangency, say right here, which make a right angle, because radii intersect tangent points at right angles, and right here. This is still part of the radius. This is also 2 inches. What I'm seeing right now is a right triangle. And in this right triangle, this length would be 4. So actually, forget what the 2 inches are. This gives me 4 inches as a whole. So in this right triangle here, let's use a different color for a second. In this right triangle here, the hypotenuse is 4 inches. And the short side is 2 inches, which is half of 4. Do you know what that means? Forget trig. This is a special right triangle. This is a 30, 60, 90 triangle, where this, and this is clearly an isosceles triangle here, but this is 30, so that would be 60 down here, and that's 90. And this is 2, then that means this here is 2 root 3. And look, this is an isosceles triangle by all natured things, so then this is also 30. So this is a 60-degree angle. I wonder if this is a, this must be an equilateral triangle. I didn't draw one, but this must be an equilateral triangle. So this is 30. This is also 2 root 3. And if this is an equilateral triangle, then everything here is bisected in certain ways. 60, 30, 30. Yeah, so these would have to be 60 here. 60 and 60. Clearly, I didn't draw it correctly with that in mind, because that 2 inches also looks significantly bigger than the others. But then that means these things are bisected. So these are also 2 root 3s. Yeah, this thing is just working out like that. So, okay. So, and this is 4 root 3 down here. I'm just going to write 4 root 3 because we need to find the base. Well, let's write 2 root 3 because that would be the radius of my cone. So I got a bunch of 2 root 3s going on. I have to remember this is not just 2D, it's also 3D. So I have the breakdown of what I would need for pretty much anything here. The radius of the cone is 2 root 3, because this is part of the great circle, or whatever. 2 root 3 inches. Slant height. Slant height would be a part of the surface area. So the slant height is 2 root 3 plus 2 root 3. That's 4 root 3 inches. If I want to find the surface area of the cone, I do pi RL, pi times radius times slant height, plus pi r squared. That's the surface area of this cone with the circle inscribed in it. Cool. I don't even think I need the sphere anymore. The sphere inscribed. I don't even think I need the sphere anymore. I needed it for all this stuff here. So this is pi times 8 times 3, 24. So 24 pi plus 2 squared is 4, root 3 squared is 4, 12 pi, which is 36 pi square inches. That's an exact, rounded, 36 pi is 113.10. 113.10 square inches. There's the surface area of our cone. The volume of the cone is going to be 1/3 area of base, pi r squared, we already saw that before, times height. What was it, 12? No, 6. Times 6. Now 6 divided by 3 is 2. So I'll get rid of that. I'll just call that 2. That's not squared, by the way. That's just a 2. 2 squared is 4. Oh, we have that. What was that number? 12 pi? So 12 pi times 2. That's 24 pi. This is cubic inches. And 24 pi, it should be 2/3 of that number. 24 pi. And I'm getting 75.398. So around 75.40 cubic inches. And that's the exact that we have there. I feel pretty good about that idea. I don't know if the idea of recognizing the equilateral triangle is immediate. I guess it should make sense. Isosceles with a 60-degree angle will work out there, but that's what I'm getting. That's what I'm feeling there on those ones. Okay, if that's the last problem, I believe so. Let's see. Yup, and guys, that ought to do it for this one. This is Mr. Robinson. Thank you so much for watching. For all intents and purposes, my movie's over. This is the last section of things that are taught, I believe. I don't think the book goes to a chapter 12 or anything, so there are other reviews to do, but this last stuff to teach, pretty expansive overall when it comes to spheres. I know they have some pretty tricky. The first part was very drill and kill. After that, they really murdered me with some of the other stuff later, and I felt like I conquered it. All right, guys, take care. I will see you in whatever next one we do. Have a good one.